Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can graph radical functions. So let's start by talking about what does a radical function look like? Well, there are lots of different types of radical functions, but in this case, we're going to be talking about the most basic parent functions when it comes to radicals, and we're going to be looking at square root functions and cubed root functions. So as we look at these two different types of functions, we're going to see that they have different characteristics. For example, a square root function, as we graph it, what it's going to do is we're going to take each number and put it in. Now, keep in mind that we cannot put a negative number in here, right? Because the square root of a negative is imaginary. And our coordinate axis here, this Cartesian plane, does not include the imaginary numbers. Therefore, we cannot put a negative x value into our function here. So the parent function starts here at 0, 0. Oh, starts right here at 0, 0. And what it then does is it then progresses past that point. So let's switch to another color. We're going to start here at 0, 0. And then as I do the square root of 1, I get 1. As I do the square root of 2, we get the square root of 2. 3, 4 will give us up to 2. And then we can go all the way up to the square root of 9, and that'll give us a 3. So you can kind of see that we have this rough sketch. It looks like this diagonal line here. And when we're looking at these parent functions here, we can see that they have some different characteristics. Now, I want to highlight specific things about this. There are a lot more to these radical functions than there are just these elements here, but there are some very important characteristics. The very first, we have this endpoint. Now, this endpoint only occurs on even numbered radical functions, and the reason why is it shows us where it stops. And so with the square root function, the endpoint is this point on the end here where we don't draw an arrow. That's where we started when we did that 0, 0. So in this case, our endpoint is 0, 0. Notice how our function stops there, or it ends, and it does not continue on past that. That's what makes it an endpoint. And that endpoint is going to vary depending on what our function does and what it looks like. Now, let's talk about the domain and range. Now, remember, the domain is the x values that we can put into a function. So it's asking us, if I put a number in here, will it give me an output? We want to know what are all the numbers we can put in. Well, we talked about previously that we cannot put a negative number into this square root. Otherwise, we get an imaginary. Therefore, what we want to do is we want to talk about all of the numbers we can put in. Well, that involves 0, 1, 2, 3, and every number in between. 0 and 1, every number between 1 and 2, things like that. And so when we're talking about our domain, really we're saying any number bigger than 0. Now, how do we write that? Well, we're going to use something called set notation to describe that. Now, when we do set notation, here's a little side note. Whenever we use these square brackets, that means that it includes that number. So if we can put a 0 in, we're going to use the square bracket. If we can use every number as close to 0 as we can get, but not actually use 0, then we put what we call a round bracket or a soft bracket. And those ones do not include the number that's written next to it. Now, a very important key here is infinity and negative infinity are always put in soft brackets. The reason why is even though we say the concept of to infinity and beyond, remember, infinity is actually a construct that says it's this very high idea that it's this concept of moving on forever. It's not actually a number. So it doesn't mean that we can reach infinity. It's something that we're going to strive to. We're going to keep going on forever to infinity is kind of this idea here. So whenever we use infinity, we always want to use a soft bracket because it's impossible to actually reach it. Because again, it's a concept. But when we're talking about the domain of this one, we're talking about what x values can I put in here? And we can put in a 0, but we can't put in anything less than that. So we're going to start with our lower bound. And this lower bound is that 0, and it has that square bracket because I can't include 0. And then what we want to do is we want to talk about what's the highest x value I can put in. Well, I can put in anything that's positive. So I can actually go all the way to as I approach that positive infinity. Now, again, we can't reach positive infinity, but I can put from any number or anything bigger than that. And when we're talking about any number greater than 0, we're going to use this to infinity. And again, infinity always has that soft bracket because we can't actually reach it. That's impossible. Now, our range is just like our domain, but it refers to our y values. So when we're looking at our y values here, what we can see is if I were to create a table of values here, so my xy table, as we were plugging things in, we got 0, 0, we had 1, 1, we had 2 square root of 2, 3 square root of 3, 4, 2, and then we kept going on until we had 9, 3. Now notice how these numbers keep getting bigger as x goes up, y goes up. Because this is going to be the case and y always will constantly get bigger, our range actually also goes from 0 to infinity. Now, one cool thing I want you to notice is how this endpoint relates to our domain and range. The x value for our endpoint is the same as the lower bound for our domain, and the y value is the same as the lower bound for our range. Now, it's not always going to be the lower bound, depending on the way that our function looks. But if it looks similar to this, those will be those endpoints. It might be the upper bound or the lower bound, but the endpoint is where our function will end. Okay, let's take a look at one other function here, and this other parent function is our cubic function. So what this cubic function looks like is we can actually put in both positive and negative numbers here. And the reason why is if you were to put into your calculator the cubed root of -8, you would see that it would be equal to -2. Because remember, -2 times -2 times -2, so -2 multiplied 3 times will give us a -8. So because it's a cubed root and we're multiplying 3 things, a positive times a positive is a positive. A negative times a negative is a positive, but a negative times a positive is always going to be a negative. Therefore, we can get negative and positives cubed roots. So we want to talk about some numbers to plug in here. Now, I'm going to plug in some pretty numbers just so that our function turns out looking good, but you could plug in any number. I'm going to plug in -8, which gives me a -2, a -1, which gives me a -1, a 0, which will give me a 0, a 1, which gives us 1, and an 8, which gives us 2. So as we graph this, we end up seeing that we have a -8, -2, a 1, 1, or a -1, -1, 0, 0, 1, 1, and 8, 2. So notice how this function, it looks like the square root function, but then it kind of flips. So it's like the square root function mirrored on itself, which is pretty cool. And so because it doesn't have an endpoint like our square root function, it has what we call a center point. And that center point is where it switches from looking like an upside down square root function to an upright one. So it's kind of that point where it almost looks like it gets straight. So in this case, our center point was at 0, 0, but that center point varies depending on what our function looks like. Now our domain in this case is what x values can be put in. Now notice how we could put in both negative and positive x values. Because we can put both of those in, our domain actually includes both the negative and positive values, or what we call the real numbers. Now this fancy scripted R represents all the real numbers or any number that's negative or positive. Now similarly, we can notice that as our x values worked, our y values were both negative and positive. So our range is actually going to be the same thing. All the negative numbers and all the positive numbers, or also known as all the real numbers. And that's kind of how we look at these radical functions. Now these two are the basic parent functions, and they are super important and really interesting. In the next video, what we're going to discuss is we're going to talk about how we can shift these radical functions based on their different components. So please check out the next video in which we discuss how we can shift these different functions.